we've developed this particle model of matter that says that matter is made up of these tiny little particles, atoms, molecules, compounds, that we can't even see. Today I'd like to set up how we go about counting these particles that are so small and so numerous, so that we have a way of counting them. The analogy I'd like to use is counting rice. When we talk about a quantity of rice, we don't usually talk about a certain number of individual grains of rice. We talk about them in big bunches. I've got a bag of rice or a cup of rice. We don't talk about individual grains. In fact, I know that in this cup of rice, there are about 8,900 grains of rice. Now, I know that because I counted them. And I didn't go through with a pair of tweezers and count one by one. That would take forever. What I did is I weighed out the total mass of the rice in this cup, and I knew what the mass of one grain was, and then I took the mass of one grain, divided it into the total mass, and I had my quantity, how much rice was in here. So what it really is a proportion problem. So what we have is, I have a proportion if I have 1 grain of rice. I found out that it has a mass of 0.026 grams. So each grain of rice, on average, has a mass of 0.026 grams. Well, if I have a cup of rice, and I weighed that out, and I found that it has a mass of 230.9 grams. 1 cup, but what's unknown is how many grains. Well, this is just a simple ratio or proportion problem. I can say 1 grain of rice is to 0.026 grams as X grains is to 230.9 grams. So we use these ratios. So 1 grain is this mass. There are how many grains in a mass of 230.9 grams. Of course, when I cross multiply and divide, I find that what I am doing is I'm taking this mass and dividing by 1, and you get a number of about 8,900 grains. So that's a much faster way of counting. An object with very small mass, and I have a great number of them, I don't talk about individual grains. You don't find a recipe that says count out 8,900 grains of rice and boil it for 15 minutes. We talk about big bunches because there's just so many. There's a lot of grains of rice in 1 cup. Well, this is how we're going to count atoms, molecules, and compounds. We are going to count them in these big bunches, not as individuals. So this is how we're going to count atoms, molecules, and compounds. We're going to take the known mass of 1 atom, or actually 1 bunch of atoms, and we're going to divide that into, or use a proportion, to find out how many atoms are in a sample. I want to count how many copper atoms are in this piece of copper. Now I have a second problem here. These things are not, this is not like grains of rice. These things are incredibly small. They're so small that if I take a very powerful microscope and look at this, all I see is the copper. I don't see the atoms. There's a ridiculous number of copper atoms in this sample. So what I have to do is, we're not even going to talk about a copper atom. We've got to count them in these big bunches. I need a big bunch of copper. So what I need is, so we're going to say 1 bunch of copper atoms. But we need to decide, well, if we count them in bunches, how big should a bunch be? Should it be a cup or a bag of rice? No, we're going to count them in much bigger quantity. So we decide, well, what should be a bunch of atoms? What do we call 1 bunch? And the way we determine it is we say, let's take the smallest atom there is, let's take hydrogen, which is the smallest atom, and let's gather up some hydrogen atoms. We'll gather up a whole bunch, 1 bunch, of hydrogen atoms. And we're gathering up enough, whatever number it takes, so that mass of 1 grams. So I'm going to get enough hydrogen atoms, gather them all together, and keep piling them up, until the mass of these hydrogen atoms equals 1 gram. And I'm going to call whatever quantity that is a quantity of one bunch. Well, it turns out that it takes 6.02 times 10 to the 23rd H atoms. That's how many I have to gather up before I even get to a mass of 1 gram. So these things are really small. Now 6.02, that's a huge number. If I were to write that, that's 6.02 and another 20 zeros. So, or 21 zeros. So if I look at that, that's a giant number. So this becomes the quantity. This is 6.02 times 10 to the 23rd. That becomes 1 bunch. We're going to count atoms because they are so small and because there's so many. We're going to count them in these bundles. And this number is so important that we say we are going to give it a name. This number is going to have a name. It's called 1 mole. A mole. So mole is just a name for a number, the same as 12 equals 1 dozen. 12 gets a name. That number gets a name of a dozen. This number, 6.02 times 10 to the 23rd, gets a name, 1 mole. Well, that number, 6.02 times 10 to the 23rd, is huge. It's so large, it's hard for the human brain to gather. How big is that number? How big a quantity is that? And the reference I use, if you look at, I had this number of rice grains, and we say, would that fill the room? And most people say, well, it probably would fill the room. Well, it would do much more than that. If I had this quantity of rice, it would cover the entire planet Earth to a depth of 75 meters. And so this number is really, it's too large to imagine for our brains to really grasp how big that is. But it is a very, very convenient number because these atoms are so numerous. We're going to say, I'm not going to count copper atoms. When I count copper, I'm not going to even count how many copper atoms are in this sample. I'm going to say, how many moles, how many of these bunches are there in this sample of copper? So what I can do is, of course, I can say, well, 6.02 times 10 to the 23rd hydrogen atoms equals 1.0 grams. And I can look at the periodic table, and we'll come to the periodic table. And I can look up the mass of copper. I now know from the periodic table it has a number there. And I know the mass of 1 mole of copper, 6.02 times 10 to the 23rd copper atoms, 1 mole has a mass of 63.55 grams. So I now know the mass of 1. One mole of copper atoms has a mass of 63.55 grams. Now I have a reference point that I can use to count the atoms in this sample. I'm going to weigh this sample. It's a little sheet of copper. And I weigh it out. 15.7 grams in that sample. And I have a proportion. 1 mole is to 63.55 grams as X mole is to 15.7 grams. And then when we solve this, we get X equals 0.247 mole. I have 0.247 moles of copper atoms. Of course, I could find out how many individual atoms is. It's very convenient to count that. I have 0.247 of these 6.02 times 10 to the 23rd. If we just take 0.247 and multiply it by 6.02, So that's how many copper atoms. So now that I've made this comparison, that's how many copper atoms are in my sample. I've actually counted them. Now this is a huge number, of course. If I wrote that out, it would take me too long. So instead of counting the atoms, let's just talk about this. This is a quantity. So we say, well, what is a mole? Well, a mole is just a quantity. I have 0.247 mole. That is how many copper atoms in the sample. In the next video, we will be counting how many compounds we have instead of just individual atoms. How do we count compounds and molecules